Assalamu alaikum everyone. I hope you are doing well. So in today's video we are going to simulate the fluidized catalytic cracking. So at the end of the video you are able to see a simulation something like this. We have a rector section and then we have a refining section. So without any further ado, just let's start. So we'll start with the new simulation, and let me show you this. Right, so the components that we are going to use today is we are going to import from the HYSYS library. So we just click on the import section, and we need to go to the library, Aspen HYSYS library. You just click on this folder. You need to go down and you need to find out this folder which just says PAKS. Click on it, and then the component list that we are going to use today is FCC component Celsius, this one. So just click on it and open this. Next, if you open the list, you can see we have all the components, starting from the light components going all the way to the heavier ends. So this is the component list that we have selected. Let's choose the fluid package. So the fluid package that we are using today is Bing-Robinson equation of state. After this we can go to the simulation environment, and the fluidized catalytic cracking you can find in the rector section. Just click on the rector section, and the one which we are going to select is this one. Just click and put it on the center. We are going to start with the new FCC units. Just click on the configure a new FCC unit. The riser we are going to select is just one. The regenerator is also, we are going to select one stage. There are options for 2 risers, 2 stage flue gas in series, 2 stage separate flue gas. However, we are going to select for today in this video is 1 stage. We also need to include the fractionator, so just click on the fractionator section and then we can click on next. It will take some time, so once it is open we need to provide all this information. I already have Excel sheet which contains all the information. I will give you this Excel sheet in the description, so you can download this one and you can use it later on. Okay, so let's start with the first thing, which is riser. So the total length of the riser that we are going to use is 119.8. All this information is provided in the Excel sheet, so please feel free to download and use it. The units that we are going to use is field units, where the length and the diameter is in feet. The temperature that later on we use is Fahrenheit, and the pressure is in pound per square inch absolute. Right, so after this we will go to riser termination section. The length is 3.281 feet. We have the diameter, which is 13.12. In the stripper section the height is 26.25. The diameter is 9.843, and the annulus diameter is 4.265. Now we can move to the regenerator section, where we have a dense bed height that is 14.76. The diameter is 24.93. The dilute phase diameter is 24.93. The interface diameter is again 24.93. You can experiment with different informations, but for this video just I use these numbers. Cyclone inlet height, that is 49.21. Cyclone inlet diameter, that is 7.546, and the cyclone outer diameter or outlet diameter is 4.265. After providing this information, we can see the next button is now appear, so just click on the next button. Now in this heat and loss zone, we are assuming that all these values, the riser heat loss, the regenerator dustbin heat loss, regenerator dilute phase heat loss, regenerator flue gas line heat loss, reactor heat loss, reactor stepper heat loss, all of these values are 0. Obviously, practically you might have some different values, but in this case we are assuming that these values are 0. After providing this information, click on the next button. Here we need to select option number 1, which is when done button is clicked, goes to the calibration environment to regenerate a new set of calibration factor recommended. So this is the recommended information, so just make sure this is checked, then click on done button. So after you can click on the done button, you can go to you can click on the return to simulation button, and you can see we are on the parent window, but we are in the sub window. So if you click on the parents window, you can go back to the parent window, and this is what we are going to simulate. However, we need to go to the subflow sheet. In the subflow sheet, we need to click on the reactor section. In the reactor section, we need to click on the feed data, and in this particular case we are also importing the feed information from the library, Aspen library. So we go to Aspen library, we need to go to let me show you how I approach this folder. So we are in Aspen HYSYS library. We click on Aspen HYSYS V11. Then we need to go to refsys folder. We need to go to refractor and then FCC. Here we need to select the feed library information. We go down and we need to select FCC feed underscore VGO. Click this one and select that one. Now we need to click on the properties window. Here again we need to select the add button. We need to make sure we need to select the riser and then accept. So after providing this information, we need to provide all of this information, and all of this information is already mentioned on the lecture in the Excel sheet that I have provided in the description. So let's start keying the information. So the first thing is the feed type, vacuum gas oil. The specific gravity that we are using is 0.9233. The distillation type is D1160. The initial point temperature Fahrenheit is 503.6. 5% point F is 635.9. 10% 681.3. Then we have 785.5 for 30%. Then we have 860.2 for 50%. Then we have 932 for 70%. We have 1023 for 90%, 1059 for 95%, and the last endpoint is 1148 Fahrenheit. The total nitrogen we have 2178 ppm watt, and the total basic to hydrogen ratio we have is 3. Sulfur content is 0.6578 weight%. Fraction of feed as processed is 0.5. The conjunction carbon residue per percent is 1.950 weight%. Then we go down all the way to vanadium, nickel, sodium and iron, copper information. So the first one is vanadium, which is 0.5. Second one is again 0.5. Sodium is 0.3. Iron is 3.5, and the last one is 0.1, which is copper. So after providing this information, we need to move to the catalyst section. Here we need to import the catalyst, and in the FCC library we need to go to the catalyst library, and the catalyst that we are going to select is AF-3. Open that. You can see all the information regarding the catalyst is mentioned here. So either you can have this information, you can generate the catalyst and provide this information. However, to save time, we already have the catalyst in the Aspen library, so we just choose that one. Close this. Then we need to click on the blend section, and here the first thing we need to provide is the weight fraction, which is 1. We have ZSM-5 additive section, where the selectivity in the blend we can mention this 0. We have heat capacities of catalyst and the coke. So for the catalyst, the heat capacity values are 0.2627. Sorry, this is 0.2627 BTU per pound Fahrenheit, and similarly for coke we have 0.3989 respectively. And then we can go to the activity section of the catalyst, and here we need to provide the equilibrium catalyst information parts per million in terms of weight. So let's start with vanadium. Vanadium is 750. We have nickel, which is 500. We have sodium, which is 2800. Sorry. We have iron, which is 4000, and copper we have 20. For catalyst inventory, we have in pounds, we have 2 e to the power 5, and for equilibrium mass percentage is 68%. After providing this information, we can move to the operation section of the FCC reactor. Here we need to provide the information for the feed, which is in volume flow barrel per day. The values are 37738 0.8. Again, these values are provided in Excel sheets. Please download the Excel sheet and you can access all these values in the Excel sheet. The temperature is 347 Fahrenheit. Pressure is 43.51 pound per square inch. And if you move to the total feed and dispersion steam information, you can go to the preheat duty pound per hour, BTU per hour, that is 0. We have the steam mass flow rate in pound per hour, this is 1.012 to the 4. We have the steam temperature, that is 392. We have the pressure of the steam, which is 145 pound per square inch absolute. After this, we can go to the riser reactor section. For the riser control outlet temperature, we have 101321 Fahrenheit. For the lift gas control section, the mass flow rate is 0. The temperature is 80.01 and the pressure is 22 pound per square inch absolute. In the reactor stripping section, we have the reactor steam temperature, that is 392 Fahrenheit. The steam pressure is 145 and the ratio to catalyst circulation rate is 3. After this, we have the spent catalyst section and the information we have for riser to regenerator ratio, that is 0. After providing this information, we can go to the regenerator section. Here we have the dense bed temperature, that is 1374 Fahrenheit. We have the flue gas, oxygen and dry basis, that is 1. We have the air volume flow wet basis, that is 147. Similarly, we have the enriched oxygen pressure pound per square inch, that is 14.65, and the temperature is 212 Fahrenheit. For the air blow discharge, temperature is 392 Fahrenheit. The dense bed bulk density is 33.71 pound per cubic feet. Then for the flow quench water rate, that is 0. So it's supposed to be 0. For quench water temperature, that is 220 and the pressure is 99.7 pound per square inch. On the right hand side, we have ambient air conditions, that is the temperature is 77 Fahrenheit and the pressure is 14.69 pound per square inch and the relative humidity is 70%. Right, after providing this information, we can go to pressure control section of the FCC unit. The reactor pressure is 49.31 pound per square inch. In the regenerator, pressure difference is 4.351. So after providing this information, we can go back to operations, go to feed, and we need to provide the information for the torch. The temperature we can provide is 347 Fahrenheit. So uh, this is converge. So you can close this window. You can see the rector part or the rector section of the FCC unit is converged now. Now let's move on to the refining section, the shortcut refining section. Here we need to click on the specs window and we need to provide the pressure information, the steam pressure information for from light ends to naphtha to LCO, HCO at bottom. So here we are providing this 14.69 pound per square inch, and all of these values are 14.69. So they are leaving at this steam pressure information is 14.69 for all of them. So after you provide this information, you can see it is immediately converge, and we have the information. So let's this is the product yield from the FCC unit, and then we have the information that is mentioned here. So if I click on the light end, I go on composition, change my basis to mole flow, or you can even use liquid volume flow. And then if you look at the information, mostly they contain light components, methane, xylene, and all the heavy components are 0. Then if you click on the second section, you can see we don't have much here. We have nothing to condense. However, if you go to naphtha, you can change the basis to volume, liquid volume percentage, and then to scroll down, you see we have some fractions between this temperature range between 110 all the way to 300 degrees Celsius. So this is the naphtha information that we have. Then if you click on the light components, liquid light components, and you can see from here we have, if you just change the basis into volume flow, this is light oil. You can see it starts from 210 degrees Celsius and going all the way to 400, or you can see even we can go to up to 430 degrees Celsius. Similarly, heavy oil, if you can click on the composition, you can change the basis to volume flow, and you can see that it mostly contains heavy oil, and the heavy oil starting from 290 degrees Celsius going all the way to 560 degrees Celsius. And the last one, which is the heaviest fraction or heavy residue, you can call. If you change the basis to liquid volume flow, and if you move all the way down to the bottom of the component list, you can see it starts from 400 degrees Celsius going all the way to 850 degrees Celsius. So this is how you can use the fluidized catalytic cracking to crack our long or heavy hydrocarbons into light to heavy hydrocarbons. So this is the end of today's simulation. I hope you gain some information from today's lecture. So if you have any questions, please feel free to ask in the description. Again, the information that is used in this simulation is provided in the Excel sheet, so you can download this Excel sheet in the description. So thank you so much for listening to me. Take care and bye.